Okay, so it's my great pleasure to introduce Chris Hoyne for the second time. He is getting into more advanced material in the second lecture, and we'll talk on central idempotents and support these days. So, Chris, your turn.
Thank you very much, George. Yes, let's just stick right in. So last time we talked about monoidal categories, braided monoidal categories, and symmetric monoidal categories. And at the last, we talked about taking the center of a monoidal category, which is a way of making a monoidal category braided, sort of furnishing it with a braiding, if you like. So today we're going to talk about the very central notion of this mini course, which is central idempotents. These are certain objects you can identify within a monoidal category that behave a bit like open sets. And today I'll be talking about, first of all, the definition of what a central idempotent is. We'll work up some basic lemmas about how they interact with each other and how they behave. And for now, I will take that to be the justification for saying they are a bit like open sets. Next lecture, we'll see that they actually are open sets in a certain sense. Specifically, I'm going to talk about support. So this is another definition we'll talk about that says where a morphism acts. So if you think about these central idempotents as sort of opens of some hidden base space, then the support is something that says a morphism or an object lives on this part of the base space. All right. Or maybe before I start, I should ask if there's any questions about last time. And again, if there's any questions during, just shout. All right, so to get us in the mood, if C is a monoidal category, then so is another category that is called the slice category of C over I, or the over category of C over I. What is that? Well, the objects of this slice category are maps into the tensor unit of the old category. So I'll typically write them the domain of this map big U, the object big U, and a map little u from big U to the tensor unit, to I. So these are the objects of the new category. The arrows between two such things, if I have an object little u going from big U to I, and a second object little v going from big V to I, a morphism in this new category from the one object to the other is a morphism between the big U and the big V in the old category that makes the triangle commute like this. Now, first of all, this is a category because if I have, I can just use the composition of the old category to compose things in a new category, and that'll be well defined, and identities as well. But the claim is it's also monoidal, because if the old category was monoidal, then so was the new category. How do I do that? Well, if you give me two objects in a new category, so a little u going from a big U to I and a little v going from a big V to I have to make a new object, so a new map into the tensor unit. What do? I take the tensor product of the two old objects. I take the tensor product of the two old morphisms. That lands me in I tensor I, and with the right uniter, I can change that into one copy of I. So now I've built a map from something into I. And you can do the same for morphisms, and that gives a well-defined monoidal category. So just to summarize this a little bit, if C is a monoidal category, then I can build a new one. That's the slice category of maps into the tensor unit. Now, in this new category, an object, so that's a map into the tensor unit in the old category, it could be the case that this object is isomorphic to a tensor product with itself. And in that sense, it could be idempotent, sort of idempotent with respect to the tensor product. And we're going to be interested in objects that are idempotent in this sense, but in a canonical way. I don't just want any old isomorphism between U and U tensor U. I want a certain canonical thing to implement the isomorphism. So that's the sort of motivation. Now I'm going to get into the definitions of what exactly I mean by central idempotent. So forget about this new category. Let's just stick with the old category. We have one basic monoidal category C. I'm going to talk about one fixed morphism little u from big U into I, and we'll say that such a morphism is left idempotent if a certain canonical map is invertible. What's the canonical map? You start at the object U tensor with itself. you use the morphism little u on the left copy to get into the tensor unit tensored with the object u, and then I use the left unit to get rid of the tensor unit. So all in all, I have a map of the type that we talked about on the previous slide, from u tensor u to one copy of u. In terms of the pictures that we were using last, excuse me, last time, that picture looks like this. I start at 2 copies of the object u. The right one I leave alone. The left one I sort of forget using the morphism I was given. Right? This little u I'm drawing as a little dot here. I'll get back to the notation. So if that map is invertible, if it has an inverse, then I'll call this morphism left idempotent. What does that mean for that thing to be invertible? Well, it means there exists an inverse. If I draw this inverse as this sort of co-multiplication picture with 1 in and 2 out, a little dot, then the fact that these two things invert each other's in pictures look like this. If I start at u, I do the inverse, and then I do the map that has the inverse. That should be the same as doing nothing on u. And conversely, if I first do the map that forgets the left copy of u and does nothing on the right, and then I sort of copy the right copy again using the inverse, that should be the same as doing nothing on both copies of u. Right? That's the pictures in the bottom left. So that's what it means for a morphism to be left idempotent. And of course, I can also say the exact same thing with everything on the right instead of the left. So we'll call a morphism right idempotent if I start at u tensor u, I forget the right copy, I do nothing to the left one, if that is invertible. Okay, so this is 2 notions of a morphism into the tensor unit being idempotent, left and right, and they're separate for now. Now I'm going to connect them. This is the definition of a central idempotent. So morphism into the tensor unit is central idempotent if a couple of things happen. First of all, I want the thing to live in the center of the monoidal category. So this is the thing we talked about last time. That means it is not just a morphism from big U to I. Big U comes with a half braiding, and little u respects this half braiding. Right? So it's a morphism in the center. And in fact, it's left idempotent in the center. So left idempotent in the sense that we just described. If I take 2 copies of this of this object, if I sort of forget one of them, that should be invertible. And additionally, I'm going to ask that it is central in the sense of the red picture on the top right. That if I start with 2 copies of u, the following 2 things should be the same morphism. The first thing is I do nothing to the right copy, I forget the left copy. The other thing is I do nothing to the left copy, I forget the right copy. So in that sense, both copies should play the same role, should be equally worthy. So if I write everything out, because I've hidden quite some things in definitions, right? This morphism has to be in the center, it has to be left idempotent, and it has to satisfy this extra centrality condition. If I write all of that out, you get the pictures on the bottom here. So starting on the left, that says that, first of all, this map that starts with 2 copies of u and forgets one of them is invertible. There is an inverse for this. That's the thing with 1 in and 2 out and a little dot in the middle. So the fact that this is a 2-sided inverse gives you the first 2 pictures like that. The red picture underneath that is exactly the centrality condition I straight up asked. And then on the right, we have these pictures with the green in them. They say something about being left idempotent in the center. So first of all, being in the center means that there is a half braiding on u, which is the topmost 2 pictures. So there is this half braiding that is natural in the sense that if I first do any morphism and then I swap u with the codomain of that morphism, should be the same as first swapping and then doing f. And the other thing is, if I swap u with a tensor product of 2 things, a and b, I might as well swap it first with a and then with b. Right? So those 2 things mean that it's that u comes with a half braiding, that it's an object of the center. And the fact that the morphism little u is a morphism in the center means the bottom right diagram. But if I first swap with A and then forget about U, that should be the same as straight away forgetting about U. All right, and that's the full definition. This is what it means to be a central idempotent. So it's a morphism into the tensor unit that satisfies these 1, 2, 3, 4, 5, 6 things. Okay. Now let's start thinking about these central idempotents a bit.
I have a question, Chris.
What way
Can we go back?
in the ring?
So, Mitya first, then I have my question. Mitya, you go.
I mean, where does this come from? Is this somehow related to a central idempotent in the ring?
Sorry, it's very hard to get feedback.
This notion of a central idempotent, I mean, is it somehow related to a central idempotent in a ring?
In some sense, you could say it's the categorification of what it means to be central idempotent in a ring, yes. And we'll see some examples.
In what way does this work?
Sorry?
And in what way does this analogy work?
We'll see some examples in a bit where this is made more precise. Let me say that for now, and after the example, we can come back to it.
My question is different. Why does the lower? So you have these pictures with the green, with the green lines in them. Why does the lowest one of these, the third one, not imply the the two ones above?
Oh, I see. I'm sorry. So the two ones above should not have the dot on the top. That's a typo. That shouldn't have been there.
Yeah, I see.
The two ones on the top should say that U has a half rating. So the left one says it's natural. There should be no dot there.
But why not? It goes to the unit object after all.
Sorry, why what?
Why no dot? There should be no dot. There should be no green dot, you say.
But
this is not the point.
in topmost pictures with the green stuff, there should be no red dots.
Why not? It goes to the unit object after all. Yeah, always had
But
red
the object, what they're supposed to say is that the object, big U, with no little u involved, carries a half rating.
Oh, I see. Okay, I see. So this is the identity morphism then, not the morphism little u.
Yes.
I see. Okay.
Sorry, that's my bad. That's very confusing, of course. I'll correct that.
That's fine.
Yes, and we'll get to this later. But first, I'll build up some lemmas before we get to examples, because I sort of lied, because I said that was the full definition, but I'm going to identify certain idempotents. Because if you have two central idempotents, the following three things turned out to be equivalent. First of all, the one factors through the other. The morphism it factors through, the mediating map is automatically unique in a way that respects the half ratings. That turns out to be equivalent to saying that if I start at U tensor V and I forget the V, that's invertible. And that's the same as saying if I start at V tensor U and I forget the V, that's invertible. So let me first prove equivalence of these three things and then look at consequences of that. So first of all, let me prove that if U factors through V, then the mediating map has to be unique. Okay, so suppose, you can't see my cursor, right? So I'll have to talk about this. So look at this mediating map. Let's say U is V after M. Little u is little v after M. Then look at this mediating map. It's something that goes from big U to big V. I could pre-compose that with first copying U and then forgetting one copy of U again. But I know that if there's another thing that satisfies the same, that also satisfies U as V after N, then I can replace the dot on U by first N and then the dot on V. So now I have copy U, do M on the one, do N on the other, and then forget the one. But on the very top of this diagram, I now have exactly two copies of V, of which I'm forgetting one. And part of my definition was that that's the same as forgetting the other one. So I can swap the dot to the other side. And then I can play the same game in reverse. I can say first m and then forgetting about v is the same as forgetting about u straight away. And then copying u and then forgetting about one copy is the same as doing nothing. So the whole thing is the same as just n. So if there's two morphisms through such that u factors through v, through these two morphisms, then they have to be the same after all. In other words, u factors uniquely through v if it does so. Okay, now let's look at 1 implies 2. So suppose that there is some morphism m such that u is v after m. I'm going to prove that big U tensor little v is invertible. I've done this by a series of pictures here. And I'll explain the pictures first, and then what they say is in the dashed green box that's an inverse for the map we're looking to invert. Right, so the left, if we start on the left, the first picture over there is I copy U, I do nothing to the one copy, and I realize that U, forgetting about U is the same as first going into V and then forgetting about V. So that's the same as just forgetting about U straight away. So first copying U and then forgetting about U is the same as doing nothing. So in other words, U tensor V has a right inverse given by this dashed box F. Now let's look at a left inverse. If I start at U times V, first I get the V, then I copy the U, then I go back into V. That's the same as first copying U, going into V, and then after all of that, forgetting about the second copy V. Now I use the centrality condition again to get the forgetting about V onto the left branch. And then I simplify everything down again. So at the end of the day, you're left with doing nothing to U, doing nothing to V. Right, so this proves that if U factors through V, then doing nothing to U but forgetting V has an inverse. And of course, you can prove 3 in the same kind of way from 1. Conversely, if you have 2, if big U tensor little v is invertible, let's say the inverse is called f, then I can just write down a mediating map that shows that U factors through v, namely the dashed box over there on the bottom right. You write everything out, and it just shows you what you want to have. Okay, so this means what I was just saying, that if you have two central idempotents, you could say that U is below V exactly when one of these three things happen. This is going to be a pre-order on the central idempotents. And I don't like pre-orders, I like partial orders. So I'm going to identify two central idempotents exactly when they're below each other. So that means by item number 1 of this little lemma, that U and V are equal up to an isomorphism of their domains, right? Just like sub-objects of the tensor unit, if you've heard about that. So all in all, if I take the set of all central idempotents of C, we'll call that Zi of C for central idempotent, that will form a partially ordered set, and the order is given by this little lemma. Now this also means that I'm justified in just drawing a little dot for the morphism little u, because the morphism a central idempotent little u is completely determined by its domain, by the object big U. All right, that's exactly what this collapse to a partially ordered set does for us. Oh, and I didn't say it on the last slide, but this unique morphism, if U is below V, that means U factors through V by some unique morphism M. That morphism is unique, so I'm justified in just drawing a little dot for that as well. So I'll draw that, you know, if U is below V, U coming in, little dot, V going out. Okay, that's central idempotent. So at the minute it's a set, and it's even a partially ordered set. The next thing is not just a partially ordered set, it is a meet semilattice, which means that if you have any 2 points in the partial order, there is a greatest lower bound between them. That's, you know, below both, and it's the biggest thing below both. And in fact, it is really just the tensor product, namely, what is the meet of U and V? What is literally, I start at U tensor V, I forget both at the same time. You can immediately see that this is below U, because that's the first line of the proof there. Because, well, forgetting about both U and V, obviously, forgetting about U obviously factors through forgetting about both u and v at the same time by just doing one of the two first. And similarly, if there's something that is below both u and v, let's call it w, then I can prove that it must be below u meet v as follows. I first copy w, then I use the fact that w is both below v and below u, then I forget about u and v. But by definition of being below, that means that I could as well, after copying w, straight away forget about both copies, which is the same as just forgetting about w in the first place. So in other words, w is below the meet, and it's actually a meet. There's always at least one central idempotent in any category, namely the identity on the tensor unit, and that will play the role of the very largest element in this meet semilattice. It might be the only one, might be lots of them below it, but it will always form a meet semilattice with one at the top. Now another little lemma that is going to make our life easier later on, namely, if you have a left idempotent morphism into the tensor unit, that's a central idempotent, and it carries a half braiding, then that becomes a central idempotent if and only if that half braiding, when you swap u with itself, that's the same as doing nothing. So in that sense, u is really central. You can give a little proof of that as well. So going from left to right, let's just start at the swapping of u with itself, and let's start rewriting it to see that we can make it into the identity on u tensor u. First, in the first step here, I'm going to use that copying u and forgetting about u are really inverses, which was part of the definition. Then I use the naturality of the braiding to straighten the two things out. So now I'm copying the left and forgetting about the right. Then you use the central property that says if you have two copies of u, I forget about one, that's the same as forgetting about the other. But now you do nothing on the right copy, you copy the left and forget about one copy. That's the same as doing nothing. So that proves left going to right. Proving right going to left is even easier in a sense, because if you have that the half braiding is actually doing nothing, then I want to prove that forgetting the left copy is the same as forgetting the right copy. Well, I just precompose it with this half braiding that's doing nothing and straighten things out. So this is good to keep in mind that central idempotents, they come with a half braiding, but this half braiding doesn't do anything when you swap the object with itself. Now, I'm being very difficult about all these half braidings and things, but if you start with a category that is braided already, then a lot of these details, if you like, about in the definition of central idempotents just vanish because of the following. If you have a central idempotent in a braided monoidal category, then the half braiding it carries must literally be the braiding that was there already. And I think that's a nice, insightful little proof, so I want to go through it. It's really a shame I can't point at things. So for this proof only, I'm going to write the half braiding slightly differently, just so it looks differently from the actual braiding. So the braiding is going to be the green over and under crossings. The half braiding on our chosen half braiding on the central idempotent, I'll write in red with a little overpass like that. So I want to prove that the half braiding is the same as the braiding. So let's start with using the half braiding to swap our chosen object u with any other object b. First step, I'll insert copying u and forgetting about one copy on the left. Second step, I'm going to use that braiding something twice, sort of on the top of each other, does nothing. So I can braid something and then braid it back. Rather braid something and then inverse braid it back. Now I'm going to use the little lemma we had before, namely that swapping a central idempotent with itself according to the braiding or the half braiding is the same as doing nothing. So I can forget about one of the two swaps I just did. Okay, then we're here. Now I'm going to use naturality to pull, if you like, the red overpass down, or in another way, if you like, to pull the green wire to the left. And then we're going to use again this little lemma that you have, that swapping the chosen object u with itself is the same as doing nothing, to get rid of this here half braiding. Now we can use naturality again to pull this dot down, and you end up with that. And now we're where we wanted, because copying U and then forgetting about one copy is the same as doing nothing. So at the end of the day, the half braiding must be equal to the braiding. So if you're in a braided monoidal category and you look at the central idempotents, you might as well just look at idempotents in the sense of, if we go back to the definition, you really only need to ask this red condition in the top right, and that thing is invertible. So you can forget about all the stuff involving the green wires here. Right. Now let's get to some examples, because that was all relatively dry theory. First example I want to talk about is, last time we had as an example of a monoidal category, a Cartesian monoidal category. So where the tensor product is actually a categorical product, a Cartesian product. For example, in the category of sets, that happened. You can prove there that a morphism into the tensor unit is a central idempotent exactly when it is a subterminal object. So by that we mean it's a sub-object of the terminal object. And another way to say that is, if you have two parallel morphisms from some object A going into it, they must be equal. Right? So there's at most one morphism going into it from any object. All right, let's see about how this works. Let's suppose first that little u is a central idempotent. I'm going to prove that any two morphisms from A to the chosen object U, let's call them F and G, they must be equal. Let's start with F. I'm going to do a very similar trick we did on the last page. Namely, first I can copy the arbitrary object A. I can do this because we have products. There is something like a diagonal map. And then I'll forget about one of the copies. Right, so I'll copy A, do F to the 1, forget about the other. But forgetting about A is the same as first doing G and then forgetting about U. Now I can use the centrality condition to swap, doing nothing to U and forgetting about U. So now the forgetting about U is on top of the F. And then we can go in reverse. Like first doing F and then forgetting is the same as forgetting straight away. And then copying the arbitrary object A and forgetting one of them is the same as doing nothing. So at the end of the day, you're left with G. So a central idempotent in a Cartesian category must be subterminal. And conversely, the converse is equally easy. If U is subterminal, we can prove that it's central idempotent. First of all, this centrality condition holds because it's clear that forgetting about two copies at the same time in either order is the same thing. And you can prove that this thing is monic. Forgetting about U is monic. That's exactly what it means, that U is subterminal. So that means I can cancel the top part here, and I'm left with the centrality condition I want to prove. Right, so in a Cartesian category, central idempotents are exactly the same thing as subterminal objects. So the definition, in some sense, of central idempotent gives a lot of extra conditions that you just don't see in the Cartesian case. So specifically, I mentioned set just now. If you take set under Cartesian product of sets, then you can prove that the central idempotents are exactly the subterminal objects. And there's exactly two of those things. Right? There's two injections going into a singleton set, namely the identity on the singleton set, 1, and the empty set going into there. So in that sense, set is very boring. It only has two central idempotents. We haven't really talked about sheaves, and that will come in lecture number 4. We'll go into a lot more detail, but I want to mention it now already as an example in case you have seen them before. If we start with the topological space X, look at sheaves over that, then it's known that the subterminal objects, and it's an easy proof that the subterminal objects correspond to the open sets of the topological space X, to the topology. So the central idempotents of a category of sheaves of sets over X are in correspondence with the topology of the space. So in this way, you can sort of reconstruct the base space if you're just given the category sheaves over X.
I have a quick question before you go on, Professor, if you don't mind.
Of course.
If you have a general Grothendieck topos instead of just sheaves on a set X, do you classify the open subtoposes of the sheaf topos in the same way?
I think so, yes. I'm
Okay.
not going to put my hand in the fire for it, but I think that's right.
Yeah, okay, so you just pick out the subterminal objects in the same sort
Yes,
of way.
exactly.
Okay, thank you.
A second example of a monoidal category that's actually a Cartesian monoidal category that we saw last time is if you start with a meet semilattice. If you give me a meet semilattice, so that's, remember, a partially ordered set that has binary greatest lower bounds, meets, in other words, you can regard that as a monoidal category by saying the objects are just elements of the pole set. There's an arrow from one object to another there's a unique arrow exactly when the one is below the other. The tensor product I can define to be the meet, and as tensor unit I'm going to take the top element. So in this way any meet semilattice becomes a monoidal category. Now if you look at what the central idempotents are in this setting, a lot of things simplify because the central idempotent is a map into the tensor unit. So in this case, it's an element of the semilattice that is below 1, below the top element, so that's any element. And all these things about being central and left and right and being invertible just come down to saying that the meet of that object, of that element with itself, equal itself. But that's always the case. So in other words, in a meet semilattice, any element is a central idempotent. So Zi of that lattice is that lattice itself. This is an isomorphism of semilattices. Now again, I'm going to foreshadow some things that I haven't really defined yet. But if you happen to know what functors and adjunctions are, the thing I just described of regarding a semilattice as a monoidal category is a functor from the category of semilattices to the category of monoidal categories. And taking the central idempotence of a monoidal category is a functor that goes the other direction. And these two things form an adjunction. Not just an adjunction, but a reflection, because if you start with what we just showed, if you start with a semilattice regarded as a monoidal category, take the central idempotence, you end up with the exact same semilattice again. So this is an example we'll think about a lot and use a lot. Here's a slightly more involved example. It's still based on order theory and partially ordered sets, but it's a bit more involved. So a quantile is a complete lattice. So that means it's a partially ordered set that has arbitrary greatest lower bounds and arbitrary least upper bounds. But it's not just that, it also comes with a multiplication and a unit. It's also a monoid, such that multiplication and taking suprema cooperate in the sense of these three equations there. Multiplying a fixed element with a soup of other elements is the same as multiplying the fixed element with each one of them and then taking soup. Right? So multiplication distributes over soup. You might not have heard about these things, but there's a lot of examples. For example, if you take two sets, your arbitrary favorite set X and Y, and you look at relations, it should be a single set X, and you look at relations from that set to itself, so subsets of X times X, then that forms a quantile because I can take the union of an arbitrary number of relations and still get a relation. And I can compose a relation with itself. Another thing I could do is, if you start with a monoid, so something that has a multiplication already, I can look at subsets of that monoid, sort of lift the multiplication to subsets of that monoid. But now I can also have unions of subsets of that monoid, so I will get a quantile. Or I don't have to take all subsets. I can start with a monoid and look at all the ideals in it. Then you can still take the join of ideals and get another ideal, and you can still multiply them. Maybe more interesting, if you start with a topological space X, I can look at its topology, so the family of all its open sets. This is a complete lattice because the arbitrary union of an arbitrary number of open sets is still open, but it also has a form of multiplication, namely intersection. I can take two open sets, and I can say their multiplication is their intersection, and that's again an open set. So this also becomes a quantile. And in fact, we'll see a lot more about this example in the next lecture. This is what's called a frame, sort of a commutative quantile, if you like, quantile with some extra special properties. And again, in the bottom of the slide here in gray, I'll say some things for people that have heard about this, but the rest can just forget. If you start with a frame, regarded as a monoidal category, sorry, every frame is a commutative quantile. If you start with a commutative quantile, you can regard it as a monoidal category, as we did in the last slide. Take its central idempotence. You won't just get a semilattice, you won't in fact get a frame. And this is an adjunction again. So the central idempotents pick out the largest subframe of a given quantile.
Sorry, Chris, I stepped for a second.
Yes?
What is a frame again?
I'm going to define it properly in the next lecture. That's why I put things between brackets. I don't want to spend too much time on it now.
Okay, sorry.
You can think about it as the lattice of open sets of a topological space, if you like.
Okay.
Or you can think about it as a quantile where the multiplication is commutative and it has one or two other properties. So in a sense, you can think about quantiles as sort of non-commutative topological spaces, and frames are like the commutative ones. I think that's, I'll put another example between brackets here. If you start with what's called an étale groupoid G, you can look at the set of all arrows of G, that will also form a quantile. And in fact, any quantile will look like that. Okay, now we come to the example that Misha, I think, was asking about. If you take your favorite commutative ring R, and you look at the category of modules over that ring, what does it mean to be a central idempotent in there? Well, by definition, it's going to be a morphism into the tensor unit. Tensor unit is the ring R itself, regarded as a module over itself. So it's an R linear map from some module into R. Now I've written out here what it means to be central and what it means to be idempotent. So the conditions of the definition are translated algebraically into the following. If you take two arbitrary elements x and y of your module, then ax times y should be the same as ay times x. And also for every element in the module, I want there to be a finite number of elements in the module such that I can write the given element as a sum of axy times yi. And finally, I want A to be sort of non-degenerate in a sense. This is the invertible condition that says whenever you have two elements of the module, x and y, then A of x times y is 0 if and only if x tensor y is 0. So this is literally what you get when you write out the conditions for central idempotent. It's not completely transparent, but there are some obvious cases. Specifically, if you start with a central idempotent in the ring R, so this is an element in the center of R that is idempotent, such as E squared is E, then E times R is an ideal of R, and in fact a sub-object of R, because I can find the inclusion of E times R into R is a good R linear map. It's a morphism in this category into the tensor unit. It will satisfy all these properties, and hence it will be a central idempotent in this category. In a sense, that's the best you can say in the general case. In general, you always have that the image of the morphism into the tensor unit is going to be an idempotent ideal like that. If your module happens to have some extra properties, for example, if it's faithfully flat or if it's free, then these are all the things that there are. So in that case, the central idempotence of your module category will be the central idempotence of the ring. So this is one sense in which central idempotents in the category, as I defined them, connect to central idempotence of a ring. There's a slightly more interesting version of this, where the correspondence is 1-to-1. Namely, if I don't look at modules over a ring, but I look at modules over a bi-algebra over a field. So now you pick your favorite field, you look at vector spaces over that field. In the category of vector spaces over that field, you take a bi-algebra. So that is these green pictures at the top, something that comes with a multiplication and a co-multiplication satisfying the bi-algebra law, and a unit and a co-unit doing the right things. So I have a bi-algebra in the category of vector spaces. I can look at modules for that for that bialgebra within the category of vector spaces, that will form a new category, modules over A. That thing is monoidal. In general, it's not braided, but it will be monoidal. So you can ask, what are the central idempotents in this category? And if you think about it for a bit, so a central idempotent in modules over A is a map into the tensor unit, which is A itself. But you can take that one step down by saying that means that it's a morphism from some object U into A, and then I can forget about A in the category of vector spaces because there's only two central idempotents there. That has to be a central idempotent in vector spaces, that composition. But there's only two such things, and you can pull that back to find out that the central idempotents of the category of modules over your bialgebra are now literally the same thing as the central idempotents of the bialgebra. So again, by that I mean all the elements of the center of the bialgebra that square to itself. So for example, to connect it back to the order theoretic examples we just had, if you take the category of complete lattices, so this is now not the category of vector spaces, but the category of complete lattices, any commutative quantile will be a bialgebra in there. So I can look at modules over it and look at its central idempotents. They will be exactly the central idempotent elements of the bialgebra. So for example, if as a quantile I take the positive real half-line, including 0 and infinity, with as tensor product plus and as ordering greater or equal, then the central idempotents have a somewhat interesting structure. I've drawn them on the right here. There's 5 of them. There's the whole set, there's the empty set. But there's also the set with just infinity in it, also the set with just 0 and infinity in it, but also the set with everything but 0 in it, so everything strictly above 0. So you can start to see some sort of topological behavior coming in here. Here's another example. If X is a locally compact Hausdorff space, then we can look at the following. This is a special kind of ring. We'll call it C0 of X. It consists of all the continuous functions from X into the complex numbers that vanish at infinity. And by that I mean, whenever you give me an epsilon, I can find a compact subset outside of which the function becomes smaller than epsilon. So it's a special kind of ring. It's what's called a C-star algebra. It has a norm in which it's complete. And what's called a Hilbert module over this ring is, first of all, it's a module, but not just a module. It comes with something like an inner product, except the inner product doesn't take values in complex numbers as you usually would in a Hilbert space, but it takes values in this ring. So I can think about the Hilbert module as a vector, and there I can scalar multiply with something in this ring, and I can take inner product of two such things and get a value in this ring again. And I ask that is complete, as you would for vector spaces. We'll see later on that the category of Hilbert modules over this ring is in fact the same thing as a Hilbert space in the category of sheaves over X, in the topos of sheaves over X. It's also the same thing as a continuous field of Hilbert spaces, in the sense that it's a continuous surjection from some total space E onto X, such that all the fibers are not just sets, but actually Hilbert spaces. And these Hilbert spaces will vary continuously, in the sense that things like the inner product are continuous, and the addition and the scalar multiplication is continuous. So you can think about the Hilbert module over C0 X as sort of a continuously varying Hilbert space over the base space X. This is a fine monodal category. You can just do, just like you would for ordinary modules over a ring and Hilbert spaces, you can take the tensor product algebraically and complete it again. That's a fine monodal category, so you can ask what are its central idempotents. And it turns out that these correspond exactly to opens of the base space U. More precisely, just as we were doing for modules over a ring R, a central idempotent is defined to be a morphism into the tensor unit. The tensor unit is the special ring C0 X. And it turns out that working out the definitions of central idempotent, the domain has to be of the form C0 U for some open subset U, and including that into C0 X. let me just point out here is that, again, we find some sort of topological nature, if you like, of the central idempotence in this category. But this category is nothing like a topos, and it's not even abelian. This is really analytic, if you like. Let me skip this example. So we've seen a lot of examples now. On the left here, I've made a little table. On the left is the category, on the right is what are its central idempotents. So if you start with a Cartesian category, you get exactly the subterminal objects. So specifically, if you start with sheaves over X, you get the opens of X. If you start with a semilattice, every element is a central idempotent. If you start with a quantile, you get the largest possible subframe within the quantile, namely all the idempotent elements below 1. If you start with modules over a ring, you get idempotent ideals and maybe some other stuff if your ring is not nice enough. But specifically, if you start with modules over a bialgebra over a field, you get exactly the central idempotent elements of A. And if you start with Hilbert modules over C0x, you again get opens of X. So in all these cases, there's definitely something topological going on in the right-hand side. That's what I want to point out here. Now I'd like to connect this topological intuition to the rest of the morphisms in the category. I'm going to say that a morphism, an arbitrary morphism F from arbitrary A to arbitrary B restricts to a fixed central idempotent if the following happens. I want F to factor through U times B, U tensor B, where I just forget about the U and then use the uniter. So in pictures, that means F has to look like this. There has to be something in the box such that F equals doing the thing in the box and then forgetting about U. You should think about this as sort of F really living only over the open set that U corresponds to. So in some examples that we saw, for a semilattice, A is less equal to B. A morphism, the unique morphism from A to B restricts to U if and only if U is below U, A is below U meet B. In the category of modules over R, F restricts to a central idempotent E times R, exactly when E times F is F. So E is a scalar here. In the category of Hilbert modules, a morphism restricts to a central idempotent over an open set U, exactly when sort of the function vanishes outside of U, in the sense that the inner product of the value of the function with itself, remember this is a scalar, so an element of C naught x, it is a function, and outside of U, so all the x is not in U, I want that thing to vanish. And let me skip this. So last time we talked about the graphical calculus having 1 dimension for categories, 2 dimensions for monoidal categories, 3 dimensions for braided monoidal categories. So we now figure out there's some sort of hidden extra dimension in here. If you start with the monoidal category C, that used to have 2 dimensions, right? And these are the sort of the green horizontal slices, if you like. We have diagrams in there as before, but there's now this purple third dimension that is the central idempotence of C. And if I have 2 central idempotents U and V like there, I can restrict morphisms to U and V. So that means I get a sort of picture like this. And you should really think about F restricts to U as saying that F sort of only lives above U, and outside of that it's empty. So I can't make this precise. This is something I'd like to do and I'm working on, to have some sort of geometry of these sorts of things and to prove a soundness and completeness theorem. But this is definitely the intuition. And this kind of restriction behaves exactly like you think it should. Namely, if 2 functions restrict to, 2 morphisms restrict to U respectively V. So if F only lives over U and G only lives over V, then their composition and their tensor product should only live over the meet. And in good tradition, I could make this into an exercise, but we could also skip that because it's really quite simple. So saying that F restricts to U means that there is a map from A to U times B, such that F is the same as that map, and then forgetting the little U. Saying that G restricts to V is the same as saying the same about there's a map from A prime to V times B prime, and then forgetting about the V. So I can just put those maps together to show that F tensor G, factors in the right way. And similarly, if I first do F and then do G, I can use the fact that F restricts to U, and then use the fact that G restricts to V, and just put everything together to find that the composition factors through U times U tensor V. So this restriction notion behaves like you think it should. If something lives over here and something else lives over there, then the combination lives only in the intersection.
Braided here, Chris, in the last proof?
Sorry?
Are we braided? Is the category braided?
Doesn't have to be. This works for arbitrary monoidal categories.
How does the morphism on the left, in the lower left corner work then?
But you have to remember that all of these U's and V's, these central idempoles, they come with half braidings.
Oh, I see. Yes.
That's part of the definition.
I see it. Okay. Mm-hmm.
So as soon as the central idempotent is involved, you can pretend everything is braided.
I see. Thanks.
So as a special case, you can ask, when does the identity on an object restrict to a central idempotent? So when does this object sort of only live over U? And you can prove that four things are equivalent, namely the identity restricts to U, is the same as saying that U tensor that object is isomorphic to that object. That's number 2 here. And you can see it in various variations, 1 and 3. The proof of this is interesting, but I think I will skip over. I'll just say that what the proof really uses is this little lemma here, saying that if something is a central idempotent, then a retract of that is also a central idempotent. That's sort of what's being used here. But yeah, the takeaway message of this lemma is you can say that an object restricts to a central idempotent exactly when tensoring with it doesn't change it. Because finally, I want to talk about support. I'd like to say what it means for a morphism to be supported on a central idempotent when it sort of lives over that central idempotent, or when it's empty, when it doesn't do anything. And to make this precise, I'm going to change the category that we're talking about, C, because I want to talk about the morphisms. So I'm going to make a new category where the objects are morphisms in C. And I'm going to say there's an arrow from F to G if the following thing happens. If G restricts to a central idempotent, then so does F. So G is sort of more defined than F, if you like. So a support datum, I will define to be a functor from that category into any complete lattice you like. So that's somehow saying that this complete lattice is an invariant for this sort of restriction notion, such that the following thing happens. If I start with a morphism, I look at what its support is. I want that to be the intersection of the support of all the central idempotents that the morphism restricts to. So this is saying that...
If I understand this correctly, in your category C less than or equal to, there is at most one morphism from F to G.
That's right.
And there may be none, so to speak, yeah?
There may be none, yes, definitely. I'm really only interested in the morphisms of C, so in the objects of C less equal. But just to make the universal property on the next page more interesting, we'll add these morphisms. Okay, so that's what an arbitrary support datum does. And again, it behaves like you think it should, like some sort of notion of support should behave. For example, if I know the support of a morphism F, I know the support of a morphism G, then the support of their tensor product, of their combination, is contained in the intersection of the two supports. And this is something you can just prove straight from the definition now. Similarly, and this is kind of interesting, the support of an object is exactly the intersection of the support of all the objects that it factors through. So in other words, the support of morphisms is completely determined by the support of objects. So if I have a map from A to B, it follows that F can only live on pieces where A already lived and where B already lived. It can't all of a sudden be more defined. So that's an arbitrary support datum. Now there is a canonical support that I'll write as support that takes values in the down sets of the central idempotents. And that's sort of the free way to make the semilattice of central idempotents into a complete lattice. What it does is it takes a morphism and assigns to it all central idempotents, such that if f restricts to some central idempotent, it has to be above that one. So this is a bit of a convoluted definition, but that's the way it works. Because what we're sort of doing is, with these central idempotents, we can only talk about opens. We can't talk about closed subsets, only opens. Now, the support of a morphism, of a function, if you like, you can sort of approximate it from within or without with opens. And that's why this implication has to be here. Yes, and this is, first of all, this is a support datum as defined on the previous page. So for this support, it really behaves like you think a support should in the sense of this lemma. But moreover, it's the initial one. If you have any support taking value in any complete lattice, it has to factor through this one. So in some sense, these down sets of central idempotents really determine sort of where morphisms live. Now, I had to do this formal completion here because, as we've seen, the central idempotents form a semilattice only, and they might not have any more structure than a semilattice. For example, we had the example of a semilattice itself. Right? So any semilattice can occur as a central idempotence of some category. You can't expect more structure. Next time, we'll talk about what happens if they do have more structure. For example, the frames that we were talking about. In that case, you can talk about the support. So now we've defined the support of a morphism as the collection of central idempotents that it lives over. If your central idempotents have something like soups, then you can talk about the central idempotent that it lives over. But that's for next time. For now, let me summarize everything I've said by saying that what have we done today? We looked at a monoidal category. We've given a definition of central idempotents in there. And we've seen that it always forms a meet semilattice. So any monoidal category has some sort of meet semilattice attached to it, but something like a space of opens, because these central idempotents behave a bit like open sets of some sort of base space. We've seen many examples, and in lots of these examples, the central idempotents literally are in bijection with the open sets of an actual base space. So you can think about these central idempotents, if you like, as a way to reconstruct from, if you just have the category, to reconstruct the base space when you weren't given the base space. And we talked about support and restriction to figure out sort of where a morphism lives, what central idempotents a morphism non-trivially acts on, restricts to. So that's it for today. Next time we'll talk about, as I was saying, so far the central idempotents are just a semilattice. Yeah, you can take meets of them, but nothing else. What happens if you can also take unions, if there's an actual topological space there? So we'll give a construction that will formally add these unions to things so that we can pretend that they always existed in the first place. And we'll see how that behaves. That's it for now. Thank you very much. I'm happy to answer more questions. Specifically, there was a question about how are central idempotents related to central idempotents in a ring? Did that example that I talked about satisfy your question?
Yeah, that's a question to you, I guess. Who is maybe no longer here, Mitya, at the moment, I see. That could be the case. So it is you can answer this right now. I think we first thank Chris for the time being. Okay, thank you very much. Mitya cannot ask any question. Are there other questions for the moment? Albertus, yes, very nice talk.
I have a question.
Yeah, then go ahead, Amy.
Thanks for the talk, Chris. first of all. My question is, has any of this been done like internally? Like for internal categories? Because you were talking
not that I know of, no.
Okay.
So if you have, you mean if you start with a, let's say, monoidal category in some V2 category?
Yeah. Yeah,
No,
I was just interested in this idea of like recovering the base space from these central idempotents. Like if I start with something internal, and there was a way to talk about like central idempotents internally, if I could recover some kind of base space, but internally still.
Mm-hmm. No, that's an interesting question. I don't really know.
Thanks.
Well, I know for certain that nothing like that has been done. So I don't know what it would look like. I think it can be done.
Further questions?
I have a question about those Hilbert version of Hilbert spaces of a synod of X. You mentioned completeness. What would that mean here? Like, how do you introduce a norm or something with respect to which it would be complete?
Yeah, that's not easy to see from this definition. So first of all, this ring C naught X is not just a ring, it's a Banach space as well, because you can talk, it has a norm and it's complete in that norm. Namely, the norm of a function f from x to the complex numbers is its sup norm. So C naught X has a norm, and that means that this inner product here takes values in C naught X, but you can sort of put a two-stage norm on A, if you like. At the first stage, it takes values in C naught X, but then you can go further and take the norm of that, you get an actual number in C. So when I ask completeness, I ask sort of if you have a Cauchy sequence at the first level, I wanted to have a limit in the second level. I hope that makes sense.
So Cauchy sequence at first level, what do you mean by that?
So you have a sequence of elements in A, such that the difference, let's call the elements little a and little b, such that A minus B in a product with A minus B, that's now a sequence in C naught X. In the Banach space C naught X, I want that sequence to have a limit. Sorry, I want there to exist an element sorry, we started with a Cauchy sequence, so let's call them little ai. So I want it to be Cauchy in the sense that little ai minus little aj in a product with itself then becomes a Cauchy sequence in C naught X. I want that to exist an element of A such that that sequence over here converges to the inner product of little a with itself. So a sequence in big A can be Cauchy in the sense that that you would expect. If you take differences of large enough elements far enough in the sequence, take their inner product with itself, that will give you a Cauchy sequence in C naught X. I want there to be a limit in A that Cauchy sequence converges to.
Converges in the sense of this two-step norm?
In the Banach space C naught X. So if you want to go one further, then you can say in the sup norm in there.
Is you happy?
I'd have to see it written. I don't understand this.
Yeah, it is. I agree. It is a bit hard to see at first point. There's a nice book by Lance, Christopher Lance. It's not very thick, and the first 5 pages tell you everything you need to know, at least about this definition.
Thank you.
Okay, further questions? If If that is not the case, then we thank Chris again and meet next time. I personally need to review the support stuff again. Chris, I have to admit this was quick, and I have not caught everything there. But as I said last time, there is a recording which I stop now. Which I stop in a second, and we will post this again, and we will post the slides too. And if so, people want to review this, they are of course invited to go there. Otherwise, we meet next Tuesday again, guys. Okay, all right. Yeah, is this fine with everybody? And Chris will now take his daughter to soccer. Okay. All right. See you guys. Bye-bye.
Thank you.